Okay, so we're going to do 14.6. So in this question, we are given a production function Q as a function of K and L equals to 9K to the power third and L to the power 2/3. So it's basically a normal capitalized production function. So the firm has already acquired the capital stock K0 equal to 1,000. Which it will not be able to vary in the short run, and it's planning to hire L0 equal to 8 staff. So part A of the question asking you to confirm that the firm will be able to produce Q0 equal to 360 units of output when its plan has been met. Okay, so basically given that K0 equal to 1,000 and L0 equal to 8, the question asking you to find out the level of output. So if we substitute Q0 and L0 back into our production function over here, we will find that Q0 equal to 9 times 1,000 to the power third and times 8 to the power 2/3. Okay, and that will just be giving you okay, so that will just give you 360 units. Okay, so part B asking you to apply the usual cost minimizing condition to calculate a factor input price ratio WK on WL. Okay, alright, so the cost minimization condition is basically where the slope of the isoquant is equal to the slope of the isocost. Okay, so it's basically the marginal rate of technical substitution equal to the negative of the price, of the input price ratio. Okay, so cost minimization condition is where the marginal rate of technical substitution equal to the negative of the input price ratio, which is WK on WL. Okay, now if again just like I have always been mentioning, if you put K first and L second, then for the marginal rate of technical substitution, it has to be the negative of the marginal product of capital first divided by the marginal product of labor. Okay, and so therefore to find the input price ratio WK on WL, we will just have to find out the marginal product of capital and labor. So if we differentiate the production function with respect to K, this is just normal. We get 9 times 1/3 of K to the power 1/3 minus 1, which is negative 2/3, and times L to the power 2/3 remain the same as constant. Okay, so we're treating L as constant when we differentiate with respect to K, and very similar for marginal product of labor. It is 9 times K to the power third, so we are treating K as constant, and times 2/3 times L to the power 2/3 minus 1, which is negative 1/3. And that is going to be equal to WK on WL. Okay, so I'll get rid of a negative signs on both sides of this equation. So now we just have to simplify this. So 9 will cancel with 9. 1/3 divided by 2/3 is going to give me a half. Now if I move L negative third to the numerator to get rid of a negative sign, and I'll get L 1/3 times L 2/3. And if I move k to the denominator to get rid of a negative sign here, I'll get k third times k 2/3, and that is equal to WK on WL. Okay, so this will just give me a half, and that will just be equal to L, and K equal to WK on WL. Okay, so we got the factor input price ratio equal to half of the L times K, L on K. Okay, say calculate the cost of producing output Q0 given the blend factor uses when WL equal to 1,000. How much profit does the firm make if the market price P0 equal to 50? Okay, so the cost of producing Q0, which is 360 units of output, is to use 1,000 units of capital and 8 units of labor. Okay, so to produce Q0 equal to 360, the firm we'll need to use L equal to K equal to 1,000 and L0 equal to 8. Okay, so therefore the cost of production C0 is going to be equal to the price of capital, which is WK, times the amount of capital used, and the price of labor times the amount of labor. Okay, so we have K0, L0. We only need to find WK and WL. So given that WL equal to 1,000, which is given to us, the only thing we have to find is WK. Okay, so if you are applying the condition that we found earlier, okay, so from part B we know that WK on WL is equal to a half of L times K. Okay, so in this case we know that L equal to 8 and K equal to 1,000, so we will have half term 8 divided by 1,000. Okay, so that's going to be 4 on 1,000. Okay, so from here we know that the values of WL is equal to 1,000, which is given to us. So WK is going to be equal to 4 on 1,000 times WL, and that is just going to be 4 on 1,000 times 1,000. And so therefore we find that WK is equal to 4. All right, so from here we should be able to find the total cost of producing 360 units, which is WK, which is 4, times K0, which is 1,000, and WL is 1,000, times L is 8. So the total cost of production is 12,000. Okay, so question also asks you to find the profit for the firm if the market price is given by P0 equal to 50. Okay, so to find the profit, the first thing we have to do is to find the total revenue, which is equal to the price times the total quantity. Okay, so 50 times 360 is going to give you 18,000. And so therefore the profit for the firm is going to be the total revenue minus the total cost. So 18,000 minus 12,000, that is going to give you 6,000 of profit. Okay, so part D, asking you to write out the firm's short-run production function and therefore the firm's short-run total cost function. Okay, so we are given a production function Q equal to 9k to the power 1 on 3 and L to the power 2 on 3. Now we know that in short run, then the capital is going to be fixed at k0. Okay, so this thing over here is going to be fixed, and L is going to be varied. Okay, so this is the variable input, and this is the fixed input. So in short run, k is going to be fixed at k0 equal to 1,000. Okay, so say in short run, k is fixed. Okay, at k0 equal to 1,000. So therefore, our production function Q is just going to be a function of L, and it's 9 times 1,000 to the power third, L to the power 2/3. Okay, so this is the production function for the firm in the short run. Therefore, we find the short run total cost function for the firm. Okay, so we know that again the total cost function for the firm C is just going to be equal to WK times K plus WL times L. Okay, now in the short run we know that K is going to be equal to K0. And we know the values of WK is 4, which is found earlier, okay, and K is 1,000, plus WL is 1,000, and times L, okay, so L is the only thing that is going to be varied in the short run, and so therefore, okay, so we get 4,000, so therefore, if we are expressing L as a function of quantity, then we should, and substitute back into the cost function, then we should be able to find a cost function as a function of the total output. Okay, so from I'll say from the start over here, I would have L to the power 2 on 3 equal to Q. Everything divided by 9 times 1,001 on 3. Okay, and okay, and we know 1,103 is just 10. Okay, so that is just going to be Q divided by 9 times 10, which is 90. Okay, so if I take the power of 3 on 2 on both sides of this equation, and I get 2 on 3, everything to the power 3 on 2, it's going to be equal to Q on 90, everything to the power 3 on 2. Okay. Now on the left-hand side, what I'm left with is L, and L is going to be equal to Q on 90, everything 3 on 2. Okay, so now I got labor as a function of quantity. If I sub that back into the cost function over here, then I will get 4,000, okay, plus 1,000 times L, and L is just going to be equal to 3 on 2. Okay, so this is my short run cost function in terms of quantity. Okay, so part A asking you to obtain the short run average total cost, short run average variable cost, and the short run marginal cost, and then draw this function and indicate the firm short run supply function. Okay, so short run average total cost. Okay, it's just going to be the total cost function divided by the total quantity. So I got 4,000 plus Okay, 1000, 90, 3 on 2, Q short run to 3 on 2, and everything divided by the total quantity Q. Okay, so that will just give me 4000 on Q plus 1000 on 90, 3 on 2, and Q 3 on 2 divided by Q is going to give me Q 1 on 2. Okay, now average variable cost. Now average variable cost is just going to be equal to the variable cost divided by the total quantity. Okay, now variable cost is the cost of labor, which is vary in the short run. So this part is the cost of capital, and that is fixed, and this part is the variable cost because that is the cost of labor. Okay, which can be varied depending on how many units of labor you would like to employ. So the total variable cost is just going to be 1000 plus 1000 on 90 to the power 3 on 2. Okay, Q to the power 3 on 2, and everything divided by Q. So that will just give me 1090 3 on 2 Q to a power half. Okay, and so lastly, the marginal cost is just going to be the differential of the total cost function with respect to the quantity. So if I differentiate my total cost function over here with respect to quantity, then I will get 1000 divided by 90 to the power 3 on 2 times 3 on 2 Q to the power half. Okay, so this is just 1000 divided by 2 is 500, so 1500 divided by 90 to the power 3 on 2 times Q to the power half. Okay, so now I would like to sketch this function on a diagram. Okay, so I just got a normal diagram over here where I have cost on the vertical, and I will have the quantity Q in the short run on horizontal and 0. So this is the cost in the short run. Okay, so I'm going to draw the average cost function first, which is this one over here. Okay, now in order to draw a graph, the easiest way is first thing to try to find the horizontal vertical intercepts, and the second thing is to find the maximum or the minimum. Okay, and so from there you should be able to have roughly the idea of how the graph is going to look like. Okay, so my total cost function in the short run, my average cost function in the short run is 4000 divided by Q plus 1093 on 2 Q to a power half. Okay, alright, so if I want to find the minimum or the maximum, okay, then the first thing I would like to do is to differentiate this and make it equal to 0. So that's the first order condition. Okay, so if I differentiate the average cost function with respect to quantity, then I will get, so this thing over here is just basically 4000 times Q to the power -1. So if you differentiate that using the power rule, you get negative 4000 Q to the power -2. Okay, okay, so plus 1000 divided by 90 to the power 3 on 2, and if I differentiate this, I'll get half times Q to the power -half. Okay, So this is just going to be negative 4,000 divided by Q square, okay, plus, so this is just 500 divided by 93 on 2 Q to the power negative half, and that I want to make that equal to 0 in order to find the maximum or the minimum, okay. So solving this equation, so if I move this negative sign to the right hand side, then I get 593 on 2 QSR negative half equal to 4,000 divided by QSR square. Okay, so if I do cross multiplication to get rid of the denominator over here, then I get 593 on 2 QSR negative half times QSR 2, and that equal to 4,000. So QSR negative half times QSR 2, that will give me QSR to the power 3 on 2, okay. And if I take 4,000 divided by 500 on 90 to the power 3 on 2, then that will just give me 4,000 times 90 to the power 3 on 2 divided by 500, and that is 6,830, okay. Alright, so in order to find QSR, I will just have to take the power of 2 and 3 on both sides of this equation. So that's become 4,000 divided by 500 on 93 on 2, and everything to the power 2 on 3. Okay, and so if you use a calculator, that will just give you 360. Okay, so that is my stationary point. So at this point, my average cost function, so if I sub 360 back into my average cost function here to find the value of it, then it's 4,000 divided by 360 plus 1,000 times 360 to the power half, and divided by 90 to the power 3 on 2. And that just give me 100 on 3. Okay. Okay, so we already found a stationary point, so this is going to be either minimum or maximum, okay. So the easiest way to get a graph is to come up with a few more points and then connect these points together to get a graph, okay. So for example, so I found that this is 360. So if I get something to the left of this point, to the right of this point, and try to see how the graph is going to look like roughly, okay. So if I, for example, take Q equal to 400, and I'll try to find the average cost, okay. So if I substitute the 400 back into my average cost function over here, which is 4,000 divided by 400, okay, plus 1,000 on 90 to power, sorry, is it 3 on 2 or 2 on 3? Okay, 3 on 2. And times 400 to a power half. Okay, then that will just give me so 4,000 90 to the power 3 on 2 times 400 plus 4000 divided by 400, so that is 33.42. Okay, why this is like 33.3, something like that. Okay, and so again, if I say I'll take QS equal to QSR, now as you can see, if it is going to 0, then because on the denominator the whole thing is going to be approaching infinity. Okay, so that's another thing you can say. So when Q is equal to 0, then average cost, so when Q is approaching 0, then average cost is going to be approaching infinity. Okay, so having known all of those information, I can try to draw a diagram. So for example, I got 360, which is somewhere, say, over here. Okay, it doesn't have to be precise, so I'll just pick a very random point. So I'll say 360 is here, and 30 something I would say is around here. Okay, so this is 100 on 3, so that's the point. And if I got 400, I would say somewhere here, then it's just somewhere here. Okay, and I know that when Q is approaching 0, my graph is going to be approaching infinity, so it's going to be approaching the vertical axis. Okay, so it's going to be something like this. Okay, so this is my average cost curves. Right, so again, it doesn't have to be that precise. We just have to get roughly how the graph is going to look like, and the most important thing is the minimum or the maximum point on the diagram. Okay. Alright, so the second one is the average variable cost, which is just a function of QSR to the power half. So that should be straightforward. Okay, so the second diagram is average variable costs, okay, which is equal to 1000 divided by 90 to the power 3 on 2, and everything multiplied by the Q short run to the power half. Right. Okay, so as you can see, the first order condition for this one is straightforward. It's just going to be 1090 3 on 2 times a half QSR to the power negative half, and that has to be equal to 0. Okay, so this equation equal to 0 when Q is equal to 0. Okay, and as you can see, when Q equal to 0, the average variable cost is going to be equal to 0. So we know that it is going to be going through the origin over here. Okay, so again, we just have to come up with a few more points. So say if I pick Q equal to 360 and C, okay, so if I pick Q short run equal to 360, which is the minimum point on the average cost function, then my average variable cost is going to be equal to 1000 divided by 90 power 3 on 2 times 360 to the power half. So I would have 1000 divided by 90 to the power 5, and that times to the power half, so that would just give me 22, so 200 on 9, which is 22.2. Okay, so I'll plot that on a diagram. So 22.2, which is say somewhere over here. Okay, so 200 on 9, which is here. Okay, so So I know that this is going to be the minimum point on the diagram because that is the stationary point that we found earlier. Okay, this is going to be the minimum, and I got another point. So if I connect these points together, it's going to be something like this. Sorry, what I want to do is, okay, and make sure that the average, so the gap between the average total cost function and the average variable cost is going to be, okay, so that is my average variable cost in the short run. Now the gap between the average total cost and the average variable cost, which is the distance over here, okay. Now the distance over here between the two graphs is basically the average total cost, and as you can see, average total cost is the total cost divided by the quantity. Okay, now we know that the total cost is 4,000, which is the cost of capital, divided by the quantity. So the bigger the quantity, the smaller the average total cost in the short run. Okay, so therefore when you draw a diagram, you have to make sure that the gap between the average cost and the average variable cost is going to be getting smaller and smaller as the quantity is increasing. Okay, so as you can see, the gap is very big over here, and it's getting smaller and smaller as we're increasing our quantity, which is what we want. Okay, so when you draw a diagram, you make sure that the distance between the average variable cost and the average total cost function is getting smaller and smaller. Alright, and the last thing is the marginal cost, which is again straightforward. So that's just going to be so it's just going to be 1,500 divided by 90 to the power 3 on 2 and q to the power a half. Okay, so it's going to be very similar to the average variable cost, but just having a bigger slope. Okay, so again, the first order condition is going to be the same, where it's equal to a half q to the power negative half, and that is just equal to 0. So again, q has to be equal to 0. And as you can see, when quantity equal to 0, marginal cost is going to be equal to 0 as well. Okay, so again, it's going to be going through the origin over here. Alright, and again, if I take q equal to 360, okay, and I'll see where the marginal cost is going to be. So I got 1,500 93 on 2 times 360 to the power half. So that's just going to be 209 times 1.5. Okay, so that's 103. Sorry, 103. Okay, which is the same as the minimum on the average cost function. So that's the point over here. Okay, so my marginal cost is going to be like this. Sorry. Okay, so this is my marginal cost function in the short run, and it's going through this point, which is okay. I'll do it a bit better. Okay, that's better. Alright, so it's going through the minimum point on the average cost, which is exactly what we want. Okay, remember, marginal cost is always going through the minimum point of the average cost curve. Okay, so that is the right thing. Alright, so I got all the cost function now. I just want to indicate the supply curve of the firm. So as you know, the supply curve of the firm is going to be we're going to be all the points where the price equal to marginal cost. Okay, so the firm is going to be maximizing. Right, so we try to find the supply for the firm. Okay, so the firm will supply whenever the marginal cost is bigger or at least equal to the average variable cost in the short run. Okay, so that's the condition for the firm to agree to supply. Now whenever the marginal cost is smaller than average variable cost, then the firm will just shut down and not supply anything. Okay, so in the short run, the firm can't exit the market. So basically the firm can get rid of all the capital and machines and everything. However, the firm can decide to shut down and not produce anything and not employ any labor. Okay, so whenever the marginal cost is smaller than average variable cost, the firm will stop producing and shut the firm down. And so that's the condition for the firm supply. And if the firm decides to supply, it will be supplying the point where the price equal to marginal cost in order to maximize the firm's profit. Okay, so this is the supply function where you equate the price in the market and the marginal cost of the firm. Okay, now so as you can see from the diagram over here, marginal cost is always above the average variable cost for any quantity bigger than 0. Okay, and as you can see from a diagram, so that is saying that the firm is always going to be supplying some positive quantity. Okay, because the marginal cost is higher than the average variable cost. As you can see, the marginal cost is above the average variable cost. Okay, so I'll say since marginal cost is above the average variable cost for any quantity bigger or equal to 0, so therefore okay, so the firm will supply positive quantity for any price, for any given price. Okay, and so therefore the supply curve in the short run is where the price equal to the marginal cost, and that just equal to 1500 divided by 90 to the power 3 on 2 Q SR to the power half. Okay, so this is the supply function, and on the diagram that is just going to be the marginal cost curve. Okay, so basically this is just going to be the curve here. Okay, so it's the same as the marginal cost curve in the short run.